Hey, we're wrapping up chapter 7. We're on 7.8 right now, simple probability, talking about probability. There are two words that you need to kind of be familiar with probability, and that is theoretical probability and experimental probability. The difference, and don't be intimidated by these somewhat big words, the difference is one is theoretically. If you answered a bunch of true or false questions and you had no idea what the answers were, theoretically you should get half of them right, right? Because you have a 1 out of 2 chance on all of them, 50-50 chance. So theoretically, you're going to get half of them right. But if I gave you a test, 100 questions, you didn't have a clue on any of the answers, and you just guessed true or false on all of them, or you flipped a coin, right? It probably wouldn't work out that you would get exactly 50 of the 100 right, would it? You might actually get 58 right out of 100, or you might get 37 right. That's called experimental probability, when you actually do roll the dice and you keep getting 2s, right? And you never get the 6 that you want. That's experimental probability. Now, if you keep doing it a lot and a lot and a lot, eventually it should average out to kind of match up with the theoretical probability. But sometimes, if there's not very many occurrences, the theoretical probability is quite different than the actual experimental probability. Right? You see the difference between those two? Hope you do. So, these words here, I'll read this really quick, but if it goes over your head, that's okay. It kind of goes over my head too, until we start to work with it. That's where we'll really get into it. So, the possible results of an experiment are outcomes. So, outcome that you're right or that you're wrong with your true-false. An event is a collection of outcomes. We'll get to that later. Once you specify an event, the outcomes for that event are called the favorable outcomes. The probability of an event is the likelihood that the event will occur. So, here's a formula to figure out the probability of an event. And this is theoretical, right? We're not actually doing these activities that we're going to be talking about. We're just going to say the theoretical probability, P, which is expressed as a percentage, which we'll find out here, is the number of favorable outcomes that you were hoping for out of the total possible outcomes. So let's take a look at what this looks like. Example number 1. Use theoretical probability to predict the number of times a coin will land heads up in 50 coin tosses. There are 2 equally likely outcomes when you toss the coin. There's heads or tails. Okay, so let's look at our formula. Our probability of getting, what's it say? Predict the number of times the coin will land heads up. Our probability of getting heads, that's why they put P parentheses heads, probability of getting heads is the number of favorable outcomes. If you flip a coin, there's only, and we're hoping to get heads, that's just one favorable outcome, right? We want to get heads. It's not we want to get heads or this or this. No, it's just heads. So there's one favorable outcome. What are the total number of possible outcomes? Well, when you flip a coin, the possible outcomes are heads or tails. So there's 2. So 1 out of 2 is the probability. And I said that they were going to put it in percent, but I think they actually leave it as a fraction. So, I see percent over here too. So we'll see what they want. Experimental probability is based on the results of a sample or experiment. You actually do that. Sorry, I'm pointing up there and you can't even see it. Experimental probability is the ratio of number of favorable outcomes to total number of times the experiment was performed. It's the same formula back here. So, finding experimental probability. You roll a number cube, a dice, 100 times. Your results are shown. Find the experimental probability of rolling a 6. All right, let's see. You roll a 1 17 times. You roll a 2 15 times. 3 20 times, so on and so forth. See that? So it's the ratio of number of favorable outcomes. Remember, a ratio I'm going to express as something over something else. Okay? Number of favorable outcomes. Find the experimental probability of rolling a 6. How many different favorable outcomes do we want? Do we want like a, I'd be happy with a 3 or a 5 or a 6. That would be 3 favorable outcomes. No. In this problem, you're happy with only one thing, a 6. Okay, so the number of favorable outcomes to you is just 1, getting a 6. So 1 over, over the total, let's see here, the total possible outcomes is 6. So you have a 1 in 6 chance of rolling a 6. This is the theoretical probability that you'll get a 6. But we actually did an experiment and we got 18 6s. So we got 6 18 times, right? And what was our total number of rolls? It was 100. So 18 out of 100. Is 1/6 the same as 18 out of 100? I don't think so. 1/6 is that. 18 divided by 100 is that. So our experimental probability actually showed that it was a little bit better odds of getting a 6 than the experimental probability. It was 18%, 0.18. The experimental probability of rolling a 6 is 18%. Starting to make some sense? So let's see, they actually just have one more example. So let's do that one. Cha-cha-cha-cha-cha. You randomly, see what I can cover up here. You randomly draw a button from a bag of red, blue, green, and yellow buttons. And here's all your buttons over here. You randomly draw 18 times. So you stick your hand in 18 times, you pull, I think, one button out, I think. Each time you record its color and place it back in the bag. There are 80 buttons in the bag. Predict how many are red. Ooh. Predict how many are red. Oh, and they give you a chart here. Oh, okay. So they're not asking you how many times did you draw a red one out. No. There are 80 buttons in this bag. You know there's red ones, there's green ones, there's yellow ones, and there's blue ones. Okay? And you just 18 times you draw some out and you put them back in. And you get red actually 10 times. You can't see inside this bag. Oh, let me show you here. You get red 10 times. Blue, you only get 3. Green, you get 3 times. And yellow, you get 2. So the question is asking, predict how many red buttons are in the bag. Are there only 10 in the bag? No, you don't know. But you know there's 80 buttons. So, find the experimental probability of drawing a red button. Well, we drew 18 times, that's the total, right? And the ratio, experimental probability, up at the top here, is the ratio of number of favorable outcomes, getting red, to the total number of times it was performed. We drew 18 times, and 10 were red. Okay, so let's simplify that. Oh yes, yes, simplify, even probability. Okay? We always simplify ratios when we can. Okay, now, if this is the probability of drawing, the experimental probability of drawing a red, couldn't we just say, if I got, like, you know, if I drew 9 times and I'm probably going to get red 5 times, what if I drew 80 times? I'm setting up a proportion here, right? Because there's 80 buttons total. So 5 is to 9. I got red buttons 5 times out of 9 draws. Well, if there were 80 draws, what would the amount of red buttons be? Well, cross multiply. 5 times 80, 5 times 80. Divided by 9, 44.44. Now, you can't have 44.5 buttons, so let's see what they say. Multiply the probability by the total number of buttons and round to the nearest whole number. Oh, okay. So they didn't even do it proportion-wise. They just say take that probability and multiply it by the total number of buttons in the bag. So basically you're finding what 5/9 of 80 is. And that's 44, because this rounds down. We got to round to the nearest whole number. Rounds down to 44 red buttons in that bag. Okay. We didn't actually dump out all the 80 buttons and count them, right? We just drew 18 times. We saw a pattern of how often we were getting red buttons. We saw in that pattern I'm calling probability. 10 out of 18 times reduces to 5 out of 9 times we're getting red. So if there's 80 total, what's 5/9 of 80? 5/9 times of means times of 80? Well, it's 44. So there's probably, according to this experiment, there's probably 44 red buttons in that bag of 80. Let's do one more. I'm looking for one that looks interesting. I think we'll go up here to 19. Toes. You survey 896 people. 409 responded that their second toes are longer than their big toes. What's the probability that a randomly chosen person from the survey has a longer second toe? Probability that a randomly chosen person from the survey has a longer second toe. Well, 409 out of 896 people said that their second toes are longer than their big toes. So we do 409 over 896, and we just reduce that. Now I'm just going to do it to percentage. I like to talk about probability in terms of percent. So I did it on the calculator, got 45 round to 2 decimal places, because that's what I usually like to do. 45.65% chance that a randomly chosen person from the survey has a longer second toe. That one was too easy. Let's try another one. Let's try 20. Find the probability of the event. Not rolling a 2 on a number cube. Not rolling a 2. Remember that the formula for probability is the number of favorable outcomes over the total possible outcomes. So the probability of not rolling a 2, on a number cube there's 6 numbers. 2 is one of those numbers. So your odds are pretty good, right? You could get a 1, a 3, 4, 5, 6. 5 numbers that you could get that are favorable outcomes. 5 different favorable outcomes out of 6. So 5 favorable outcomes out of, now where am I getting this? You might have to flip the page back, right? Number of favorable outcomes over the total possible outcomes. When I roll a dice, the total possible outcomes is 6. So that total goes on the bottom. The number of favorable outcomes in this case, not rolling a 2, is 5. So there's my probability. 5 out of 6. And I think that is going to do it. So, we'll end a little early. Have fun with probability. Talk to you later.